All right, everybody, we're going to go ahead and get started. First off, thank you for coming to this talk. My name is Donovan Fritz. I'm a Cloud Network SRE on the Cloud Networking team at Netflix.
Hi, my name is Joel Kadama, and I'm also a Senior Cloud Network SRE on the Cloud Network Engineering team, and we're going to talk a little bit about what it's like to be on this team. And unfortunately, like my counterpart on the core SRE team, I don't have any Netflix shoes. But those of you that saw them, they're stickers at the booth, so feel free to go get them. So in traditional Netflix ways, we're going to start off with some numbers. 109 million. Raise your hand if you understand the significance of this number to Netflix. Anybody out there? This is actually the number of global subscribers that we have, and hopefully that encompasses many of you out there. 1 million plus. This is actually the number of requests on average that we receive per second from those 109 million subscribers from a multitude of devices. You think about connecting from your phones and laptops and tablets and TVs and streaming sticks and every other device that plays Netflix out there. And this is important to us. 150,000 plus. This is the number of EC2 instances we're running at any given time to be able to power our microservice architecture that is able to service those million plus requests per second. 75 plus. This is the number of accounts that we currently leverage. And for some of you, this may be small. I know some people have hundreds or thousands of accounts, but we represent 75 of highly densely concentrated compute in those 75 accounts. 4, this is the number of AWS regions that we currently use. 3 of them primarily for our streaming service, with an additional region that we use for lots of our tooling as well as some supporting business applications. Now, as far as our AWS infrastructure is concerned, all this lives in VPC. But for those of you that know, that wasn't always the case. Right? A lot of our microservice were actually rooted in Ec2 Classic. How many of you remember Ec2 Classic? All right, good number of you. Well, if you remember, Ec2 Classic was a flat, very open network utilizing the 10.0/8 space for every customer. So that means if I launched an instance and several of you launched instances, they were all in this simple network, right? Utilizing this 10/8 space. And for our developers, it was easy for them. They didn't really have to worry about how they interacted with this underlying infrastructure at all. But that lacked several aspects of VPC that we wanted to utilize. Things such as enhanced network performance or newer instance families, and as well as the security to be able to not expose our instances out to the internet. And because of this, we really had an initiative to move all of our services from Ec2 Classic over to VPC. Now, when you think about VPC, there's much more complexity involved in it. And due to that complexity, it really required us to form a team that was out there to be able to create, manage, and evolve our entire VPC infrastructure and think about how we are going to scale that infrastructure for the next 100 million customers. So out of this formed a cloud network engineering team. How many out there actually work on this? How many of you out there are in charge of managing VPCs and thinking about evolving that architecture? Oh, great, great, good number of you. So when we took on this ownership of this migration project and we had to think about how do we get to the point where we can migrate all of our services over into VPC and how can we scale that up? We really wanted to keep it simple. So we decided to go with a general deployment, which is a public subnet and a private subnet per availability zone. And we utilize NAT gateways for that. It's a very simple architecture. It allows us to kind of stamp these out, duplicate them across all the accounts we're going to need to deploy into. Now, when we expand this out to the regional level, you think about Ec2 Classic and the fact that it was all in this very flat network, so every instance could talk to every other instance. When we moved to VPC, we needed to provide that same level of connectivity. And really, in order to do so, that meant we had to peer all of our VPCs together. In the end, this ends up with the full mesh peering, very similar to how Classic worked. Now, if you continue to zoom out to a global level, we still needed to have connectivity regardless of what region it's in. And in order to do so, for the public side, we generally use internet. For the private side, it meant that we needed to have some connectivity around our private subnets. And this meant creating our own MPLS backbone. And we really used Direct Connect for this connectivity itself. Now, when you think about this architecture, it's pretty straightforward. We try not to make it complex, because that added complexity, it just makes it harder to manage and deploy and think about maintaining some consistent configuration amongst all of our VPCs and accounts out there. This straightforward architecture allowed us to migrate all of our services from Ec2 Classic over to VPC, which took us about 6 months. We completed this last year, Q4 of last year, and we've been in VPC for roughly a year now. Now, for those of you that were here last year, we did a presentation at reInvent talking all about this journey, right? All the things that we had to go through in order to be able to migrate our service over into VPC. And there's a couple things we learned about that. First off, global unique IP space is good, right? We needed to have global connectivity without added complexities of having to translate in between overlapping IP space. And so it's important for us to have this global unique IP space and enough of it to be able to grow and scale to be able to support our next 100 million customers and beyond. Now, due to the fact that Classic uses a 10/8 space, we couldn't leverage that. So we decided to go with the next largest pseudo private IP space, RFC 6598, which is basically 164/10. This provides us roughly 4 million addresses that we can use to slice and dice across all the VPCs and accounts that we are going to need. Now, one thing we learned out of this, though, is that IP management's hard. How many of you out there have a past in traditional network engineering? And how many of you want to be able to kind of segment your environment with network space so you understand what's going on by looking at the IP address itself? Me too. That's tough, right? And in the cloud, you can't really do that. Like I said, we use public subnets and private subnets. We don't have real segmentation. So forecasting and IP management is something that's very difficult to do. But when we looked at creating our VPC architecture, thinking about how we were going to grow, we tried to forecast that. We tried to predict, okay, these VPCs are going to need this much IP space. How many of you have gotten that wrong before? Yeah, me too. Luckily we have some tools around the ability to monitor our IP utilization. We constantly poll all of our subnets and we look at how many available IPs are there, and we pump this into Atlas, which is our time series metric collection system. And here we can actually plot this. And we look, in this case, at our % of utilization of subnets over a time span. In this case, we're looking at one account and we're looking at a particular region, US West 2. On the left-hand side, you can see that % of utilization. And the bands across the top actually represent our private subnets and our public subnets. Remember, we have one per zone, so you kind of see 3 lines kind of closely together. If you notice on the left-hand side there, we're pushing the bounds of 60–70% utilization. And for us, that's a concern, especially as we move into holidays. How many of you are sitting around the holidays watching Netflix? Yeah, me too, and a lot of people are, which means that our service has to scale. And in order for our service to scale, that requires more IP addresses. And as a member of the cloud network engineering team, it's my job to ensure that they can scale. Luckily, Amazon released a feature called Vpc Resize. And this feature allows you to add additional CIDR blocks into a VPC. You can see around November 8th, we added the new CIDR block, and as applications redeploy, they pick up these new subnets. Right, and you can see they start to utilize IPs in these subnets, and eventually these will kind of converge, so they'll balance out. Now, in addition to monitoring our IP utilization, we also do things like monitor our infrastructure. We actually poll our VPC configuration every few minutes, and we perform diffs against previous and current configuration. This allows us to see changes within our network itself. And this is important because Amazon doesn't always provide a change event for everything that's changed within our environment. In this example, we're looking at the fact that we have route propagation enabled on VGWs. And because we use Direct Connect out there, new routes might get propagated into that network. And I want to be informed when they do. So I can get these notifications that tell me, hey, these routes were added. And any other changes that might happen in VPC, we can also be alerted. Now, not only do we monitor our infrastructure and in charge of our infrastructure, but we're also responsible as a team for DNS. And not only for creating records and managing zones, but we're more in charge of thinking about the performance and availability of DNS itself. You know, when you think back to those millions of requests per second that are processed, all of those start off as a connection to a host name, whether it's an API, whether it's our web service, right? And we're in charge of you from going from connecting to Netflix to actually watching Netflix. So it's important to us how well you actually can connect to those DNS servers. Can you? And what's the performance of that? Now, to gather some insight into that availability and performance, we've instrumented some DNS monitors across our different platforms, including iOS and Android and website, and it allows us to start to understand some of the DNS latencies we see. See, in this case, we're gathering all that data from different networks out there, represented by these numbers. These numbers are ASNs, right, autonomous system numbers, or representing networks in the world. And in this case, we're plotting this against our median Route 53 latency based on those numbers. You can see across the bottom, there's several different countries out there, including US and Mexico and France and Great Britain. You can see across the left-hand side, there's latency in milliseconds. The nice thing here is we get to see the density of these DNS requests. Those bubbles, the size of them, represent the number of requests we're seeing. Now, generally, let's take US for example. US sits at median around 100 milliseconds for DNS response. If you notice that bubble on the top right-hand side, looks pretty bad, right? It's sitting around 800 milliseconds. It's basically 8x what the median latency is for US. And these are things that we can gather insight around and drive a resolution to them. And in this case, due to our great relationship with Amazon, we can provide them this data, talk to the Route 53 team, and say, hey, you guys, we see that there's a problem with this ASN, and we can drive a resolution to that. The nice thing is that not only fixes it for us, fixes it for everyone else on that network, so you're welcome. So in addition to thinking about things like infrastructure and DNS, we also want to get some network insight. Right? As an operator or an SRE within our organization, you know, I'm commonly posed with questions that I want to be able to answer, such as, does anyone know if there are any kind of network weather events going on in US East 1? We've seen a couple of hosts running network partitions. Or, hi there, can someone help me resolve a network connectivity issue between one microservice or another? Right? These are common questions. I want to be able to answer them. And in some cases, they may not even be questions, but statements around network health. I'm thinking this might be due to some networking unpleasantness, or I'm seeing what seems to be network-related errors on startup. And the biggest thing for me is, how do I answer these? VPC is a black box. You don't really have a lot of insight into the network, but we want to extract some. We want to gather some information about this. So what do we turn to? Well, one of the advantages when we moved into VPC was this ability to have flow logs. Right? These flow logs are records of traffic flow within our environment between our applications. And we found that flow logs are really good. You know, they're a canonical source of this information. They're given to us in a semi-timely manner. But as we started to look at those to start answering some of the questions, one of the things we realized is that flow logs are really good, but really good meaningless data. They're IPs talking to IPs. Right? Remember, we're big and dynamic. Our IPs change all the time. It's very difficult to determine what those are. So Donovan, you've done a lot of work, you know, looking at VPC flow logs and trying to identify some of the problems around them. You know, what are some of the things you've seen?
Absolutely. Thanks, Joel. Again, my name's Donovan Fritz. I'm another member of the cloud networking team at Netflix. I've spent a lot of time looking at VPC flow logs, and I think Joel hit the nail on the head here. When you really start looking at VPC flow logs and diving in and trying to derive some insight from them, they're really meaningless in the end, and that's because they lack context. So who here has seen a VPC flow log record before? Let's see a show of hands. Awesome, a lot of you. It's exciting, super exciting. Okay, so this is the VPC flow log record from the Amazon help site. And we can see, based in this example, there are two things communicating. There are the two IP addresses in there. And so we see two things communicating inside VPC. We see .139 in blue and .21 in green. But the problem is that I have no idea what these are. These are two IP addresses communicating inside VPC, but Still, having this information means absolutely nothing to me. As Joel mentioned earlier, in typical networks, we have the idea of network segmentation. In a lot of networks that I've worked in the past, it's really common to be able to look at an IP address and understand that it's a database in this data center. Or this IP address looks like this, so it must be an Active Directory server in this corporate office. In the cloud, we don't have any of this network segmentation. Again, our service was forklifted from Ec2 Classic into VPC. That means that our VPCs end up being these large flat IP spaces. And they contain all of our resources. Now, most of the time, these resources are EC2 instances that we have a lot of control over. But VPCs will also contain resources that we don't have a lot of control over. Services like load balancers, Elasticache, Lambda, ALBs, RDS, all these services live inside of our VPC. They all have addresses within our VPC address range. And so when we see these addresses communicating inside VPC, we want to know what they are. Now, this isn't a problem with just things inside of our VPC, but also services outside of our VPC as well. So Amazon SQS, or the Simple Queue service, is a great example of a service Amazon offers that lives outside of our VPC. It's still in AWS, but not in our VPC within AWS. Now, typically when we interact with SQS, we use the provided SDK. Under the hood, that SDK resolves a host name. That host name resolves to an IP address. And so when we look at network level information, like what we have in flow logs, we see this IP address show up. And we want to know what it is. So if we're trying to figure out a question that we want to have answered, what are we really trying to get at here? We want to know what application has these IP addresses. But it's actually a lot more complicated than that, as we've discovered. And this question isn't quite good enough, and we're going to update it in a second. And the first big challenge that we ran into was that IPs change a lot. So if you think about a journey of an IP address through time, at some point in time, let's say T1, that IP address could be assigned to an EC2 instance. If that instance is stopped, terminated, if for whatever reason it stops using that IP address, it's free to be used by something else. At this point in time, I like to think of the VPC as a bucket of tokens, and IP addresses are the tokens within that bucket. Now, in order to communicate on the IP fabric that is VPC, you need to hold on to a token. That token is yours and only yours to communicate. And once you're done communicating, you put it back in the bucket, and it's free to be used by something else. Once this instance is done with this address, it can be picked up by something else, another resource. It doesn't have to be an instance. It could be something that we have little control over, like a Lambda function. This Lambda function can live in our VPC, and it can take that token from that bucket and use it to communicate. And when it's done, it'll put it back into the bucket, where that IP address is then free to be used by something else, like another EC2 instance. Could be another Amazon resource as well. Just the dynamic nature is what's key here. And again, in our environment, this happens a lot. So we're looking at that same graph that Joel had showed earlier of our IP utilization. And again, we have our time on the x-axis, which is the 2-week time span, and our percentage of utilization on the y-axis. But what's interesting here, and something different that I want to point out from Joel earlier, are these sharp increases and decreases. Now, these big changes are actually an artifact of how we deploy software at Netflix. At Netflix, when we deploy software into production, we put that software onto a new EC2 instance inside of a new auto-scaling group, and we bring that auto-scaling group to the same size as the old one, shift traffic over, and then decommission the old ASG. And so when we have very large clusters doing software deployments, we have a very large influx of IPs suddenly being used. And then when that old cluster is done, all the traffic is shifted over, we have a sudden influx of IP addresses suddenly not being used. This just goes to show how much IP addresses change in our environment. So when we bring back our question from earlier, we need to add in this temporal component. We need to think about this in terms of time. We want to know what application or service had these IP addresses at this time. Because again, when we see these IPs in flow logs, we don't really care about the address. We care about the service or the application. We want to be able to tie that flow log record back to a longer-lived entity, again, like an application or a service. But even this question is not quite good enough. As Joel mentioned earlier, we have globally unique address space in our environment, but we're not perfect. We do have corner cases where we do have overlapping VPCs. And as somebody with a strong networking background, I consider overlapping IP space to be in the same routing domain. So if we update our question one more time, we need to add in the routing domain. We want to know what application had these IPs at this time in this routing domain. And this is really the first big challenge with VPC flow logs. The IP addresses mean nothing. So we're going to go back to our VPC flow log record example again, and we're going to look at another big challenge. So with this flow log record, again, we see two things communicating here, but we don't know who's talking to who. We don't know if it's .139 talking to .21 or the other way around. These records are stateless. So if we look at the TCP port numbers within the flow log record, it's easy to see that .139 was sending traffic from TCP port 20641 going to TCP port 22. And we're in Vegas, so if I'm going to make a bet as to which one's talking to which one, I would say this is SSH traffic from .139 going to .21. But if we change the port numbers to something a lot less obvious, it's much more difficult to see what's going on here. In this example now, I've changed them to TCP port 11211 and 8008. Now, if you're a networking nerd like me, port 11211 would set off a light bulb, and you would think that this must be memcache. This must be .21 speaking memcache to .139. But if we consider what these IP addresses are actually assigned to at this time, this doesn't make sense. This is a classic, if .139 is a classic load balancer, this example kind of breaks down. This classic load balancer could be fronting a memcache cluster, but we don't do that in our environment. So now our assumptions about trying to derive directionality from a state list of VPC flow log record is absolutely incorrect. What was actually happening here is that this is HTTP traffic over a non-standard port. And the classic load balancer just happened to choose a source ephemeral port of 11211 that just happens to overlap with a well-known service. So we can see in this example that making assumptions around TCP port numbers is problematic. It's so problematic, in fact, in our environment, we don't even do it. So the next challenge that we kind of run into with VPC flow logs is that they're fragmented. And fragmented is kind of an interesting term, interesting word choice. Let me show you what I mean. So if we look at a connection between two EC2 instances inside VPC, this could be anything. It could be one microservice talking to another. It could be nodes in a Cassandra ring replicating data between each other. If for whatever reason we have two instances inside a VPC community or sending traffic, we actually get 4 VPC flow log records. And this is an artifact of how flow log records are generated to begin with. In VPC, flow log records are generated by ENIs, or elastic network interfaces. Again, they're stateless, as we just mentioned, so we'll always get one record for traffic out and one record for traffic in. And we see this on both sides of the connection. We have 4 VPC flow log records now describing this one TCP connection. Now, I'll call that easy mode. It's not quite fragmented yet, but if we step up to what I'm going to call medium level difficulty, it gets a little bit more interesting. Now, the same green instance, the information around that stays the same. One record for traffic out, one record for traffic in. But as this connection traverses a NAT gateway to an external service like Amazon SQS again, we actually see more VPC flow log records as it traverses a NAT gateway, since NAT gateways live inside of our VPC. And since they live inside of our VPC, they have ENIs. And since they have ENIs, they generate VPC flow log records. So NAT gateways, the purpose of a NAT gateway is to NAT traffic. So we see flow log records pre-NAT and post-NAT. For the pre-NAT VPC flow log records, it'll actually look like the instance is sending traffic directly to the NAT gateway. So the layer 3 address that we see inside the flow log record will be sourced from the instance's private IP going to the NAT gateway's private IP. And then we see the opposite for the other side of the stateful connection. And on the post-NAT side of the traffic flow, we see something very similar. We see traffic sourced from the private IP of the NAT gateway going to the public IP of Amazon SQS. Now, This is what I call medium level difficulty. And it gets even more interesting if we replace SQS with a classic load balancer. Okay. Now, in this particular example, we're replacing the SQS with a classic load balancer. And since load balancers terminate TCP connections and they need to service that connection to a backend instance, this now one service call generates 2 TCP connections. So since the classic load balancer is something that lives inside of our VPC, it has an ENI and it generates flow log records. And since it generates flow log records, we see the traffic from the NAT gateway now going to the classic load balancer, like that. And what's interesting about these flow log records is that they're going to show the exact opposite of what the NAT gateway shows. So again, the NAT gateway will be coming, the layer 3 addresses inside the flow log records will come from the private IP address of the NAT gateway going to the public IP address of the classic load balancer. And the classic load balancer now will actually show the opposite. It will show the public IP address of the NAT gateway going to the private IP address of the classic load balancer. Now, since this classic load balancer has to respond to this request via this backend EC2 instance, we'll see flow log records describing that traffic flow from the classic load balancer's perspective and from the instance's perspective. Now, this is a fairly complicated example, but this is actually something very common at Netflix. If you consider Atlas, our open sourced monitoring system, this is what it looks like when it publishes traffic cross-region. We actually see this exact same traffic flow in our environment. In this example, we have 2 TCP connections and 12 VPC flow log records. Now, did everybody follow exactly what I just said? Okay, so there's some smart people out there. We got a few hands. But the point is that this is complicated. We have all this complexity, 2 TCP connections, 12 VPC flow log records, NAT gateways, load balancers. We have all this complexity, and all I'm really trying to answer from VPC flow logs, all I really care about is that the green instance was communicating to the service in white. Now, the last challenge with VPC flow logs has to do with our scale. As Joel mentioned earlier, we operate in 4 Amazon regions. We have 75 accounts, over 75 accounts. We service over 1 million requests from our customers every single second. And at any given time, we have well over 150,000 EC2 instances online and running. This all totals for up to 10 million VPC flow log records every single second. So if you really think about that, in the time that Joel and I have been up here talking, Netflix, as a company, has generated well over 1 billion VPC flow log records. So now, I talked about the challenges quite a bit. Let's go through the solutions. How are we going to solve each one of these challenges? For the first one, if you remember, we left off with this great question. We wanted to know what application or service had these IP addresses at this time in this routing domain. I think this is a really great question to ask, because it has specific inputs and it has specific outputs. It's a function. It's a function we can design and build a system around. Given a routing domain, an IP address, and a timestamp, tell me what application or service had that address. The system that we've been working on internally to answer this question is called Sonar. Sonar works like this. It's broken down into 3 phases: extract, transform, and load. So we extract data from CloudWatch events, from our own internal Netflix events, and then we transform them into other events, and we transform them so that everything is in the context of an IP address. We take these events, and then we send them into another data stream. This data stream, we call it an IP change stream, and we call all the events IP change events. So this data stream now is our canonical source of truth for what happened to an IP address over time. This data stream will dictate any time something changes to an address. So if a private IP address was assigned to an ENI, a change event is generated. If that ENI is attached to an EC2 instance, a change event is generated. If a Titus container uses that private IP address, which is on an EC2 instance, which is using that ENI, a change event is generated. Now, Titus, for those who may have never heard it before, is our container platform at Netflix. So we don't live in a perfect world, and unfortunately, we can't make everything event-driven. So there are still some cases where we have to do some polling methodologies. We have to pull the Amazon API. We have to pull our own internal APIs and some of our own internal logs. And then we have this really fun DNS crawling technique. And we take these data sources and we pull them at regular intervals. And so for the DNS crawling technique, what we do is we think about that Amazon SQS example. We're trying to track something that is virtually intrackable. So what we do is we generate all the host names that all the Amazon services use. So the host name that the Amazon SDK will actually use under the hoods, we resolve that over and over and over again, and we catalog the changes over time. And then anytime we detect a change, we then put it in this stream as well. So this is really great because we have this data stream that depicts things inside of our VPC, but also things outside of our VPC, but still in Amazon. So anytime SQS uses a new IP address, we add a change event. Anytime another Amazon service, SNS is another great example, the simple notification service. Anytime we detect an IP change there, we also put it into this change stream. So that's great for IP addresses. Now we have metadata around IP addresses. We can answer the questions that we were asking before, but what do we do about the stateless problem? So what we do is, remember, we ran into problems and we had some challenges around being able to deterministically deterministically figure out the state of a connection based on a stateless VPC flow log record. And so as I mentioned earlier, we don't guess around port numbers. We want to know for a fact. So what we do is we run our fleet of EC2 instances and we run the Amazon SSM agent on them. This SSM agent is then responsible for telling us which TCP or UDP port numbers that particular instance was listening on. And then we get this, we process this, and we store it into a key value store for a later lookup. So the fragmented problem. If you remember, things got pretty interesting. We had one service call going across region, 2 TCP connections, up to 12 VPC flow log records, ton of complexity. How do we solve this problem? The truth is, we don't. We live with it. This is a known deficiency. And it's something we need to be really cognizant of, because when we start looking at the data, as we're going to show later, we need to understand how the data is being generated from flow logs, and it's going to make sense, and we're going to see how the known deficiencies actually play out when we're looking at the data. So now for the last solution. Again, this has to do with our scale. How do we, as a company, crunch through all these millions of VPC flow log records every single second? The system that does this internally is called Dredge. The way Dredge works is it assumes that IP change events from Sonar and VPC flow logs are both infinite data streams. And what Dredge does is it takes the data from both those streams and it performs joins on them. And then the output of this is it would create what we call enriched VPC flow log records. And these enriched VPC flow log records are put into yet another data stream. And we leverage our internal data pipeline, our already built infrastructure for handling large amounts of data. We leverage that for all of our enriched VPC flow log records. The data pipeline team is then responsible for managing all those events and routing them into a Druid cluster. And for those who have never heard of Druid before, Druid is a column-oriented distributed data store. And the reason why we use it is because it really excels at fast interactive queries. Now, before I continue, I need to mention that our colleague, John Bennett, is going to be presenting on this system in much more detail tomorrow. His talk is in the Analytics and Big Data tract. It's session number ABD401. I encourage everybody to go view his session as well. It's tomorrow at 4 o'clock. Again, ABD401. So now, as I mentioned, Dredge needs VPC flow logs to be in a data stream. We use Amazon Kinesis for this. And the way we do this is we enable VPC flow logs at the VPC level. The flow logs are then sent into a CloudWatch log group. We use cross-account log sharing to aggregate all of our VPCs across all of our accounts into a centralized source, into a centralized account rather. Once in the centralized account, we then aggregate them across all the different regions into a centralized Kinesis stream. So now that we have all of these flow log records in a centralized Kinesis stream, we need to join the data with the IP change events. So it's going to get really fun here. So if you remember, we have our 3 pieces of information that we need from Sonar. We have the routing domain, the IP address, and the timestamp, all present in the VPC flow log record. Now, technically, the routing domain isn't the account number and the ENI ID. We have to do another lookup to derive the routing domain. But given any account number and ENI ID in our system, we can deterministically make that lookup happen. So we have our Sonar function, domain, IP, time, tell me what application it has. We take the IP address and the start timestamp of this flow log, and we plug it into this function. And we get back our application that held that address at that time. So in this case, we're getting back foo and bar. Now, we need to determine the state of the connection. Was this foo talking to bar, or was this bar talking to foo? So again, we have to use that key value store, that memcache data store that we had created earlier. And this will deterministically tell us if that instance was listening on that port. So in this example, 20641, IP address .139, it was not listening. So I won my bet from earlier. This is in fact .139 talking into .21. So now we know for a fact that that was the direction of the traffic flow. So now what we do is we take these new pieces of data, along with a lot of the old pieces of data, and then we mutate them into a new data structure. And this new data structure is our enriched VPC flow log record. And again, we just simply put that enriched VPC flow log record and we hand it off into our big data platform, our internal data pipeline, where that team is then responsible for managing the data and routing it into a Druid cluster. Whew. Joel, we went through a lot of effort to enrich VPC flow log records to try and derive meaning. What do we get from all this effort?
Good stuff, Donovan. Thanks. You know, you left off with me talking about how we gather some insight into the network that is VPC, and we did all of this, enrich these flow log records so we could start to actually gather some information. But you know, if we take a look at historically how we gathered understanding of application dependencies, you know, we used to rely on request tracing. Like many application developers, you know, we instrument request tracing to understand what is it from an application that you depend on. And if we take an example, and in this case, we have our UI visualization tool here that shows an application themis on the left-hand side, and really its only dependency from request tracing is a Cassandra cluster. Now, as a network person, I can assume that this is not the only call that's being made. There's got to be something for you to call Cassandra to begin with. Yeah, something that may generate that call. And since we know that the network never lies, we can utilize flow logs to look at all the different calls out there. So if we take the same visualization and pump our enriched flow logs into this, we can actually see that there's a ton of other dependencies that are out there. And these may not be application dependencies, but they are network dependencies, right? So we can see Themis talks to SSM, it talks to Cassandra, it talks to Route 53, as well as several other internal applications out there. And so this is some of the power that we have by gathering these enriched flow logs. It helps us, you know, tell developers, hey, you have many more dependencies than you really think. And especially when it comes to troubleshooting an application, this is a good place. Like, hey, who do you talk to? Where do I need to actually troubleshoot? Now, we talked about Druid. Druid excels at these, you know, high, you know, queries. And one thing we laid on top of that is Swiv. Swiv is a UI visualization tool. And if we take the same kind of approach of what we just saw, looking at Themis, we can actually see from our UI here, not only do we get to see the local app of Themis, the directionality of the traffic being out, as well as the splitting on the foreign application, we can see that Themis still talks to all those, but we get to see bytes, volume, bytes, flows, packets, how much data is going to these different applications to determine, you know, how much of a dependency is that. Now, if you look on the left-hand side, we have several dimensions we can actually slice on. And one of the nice things about Swiv is it's fast, right? When you lay this on top of Druid, Druid excels at that fast query analysis. So we can take any of this data that we have, and within seconds, we can actually analyze from any of these dimensions. And if you notice, we have things like time, we have actions, which this is valuable. One of the pieces of VPC flow logs that you get is it's really the only thing that can tell you whether a security group accepted or rejected that traffic. right? We then have things such as, we split it on foreign and local. And in those kind of elements, we have things like clusters, applications, regions, VPC ID, and we can filter on any of these, and we can split on any of these dimensions, as well as understand it volume-wise from either a bytes perspective, a flows, or an overall packet perspective. So when you look at things, what does this really provide to us? At a business level, we can start to see things like how much traffic is going between our regions, right? We do have global connectivity, and we want to understand what is that traffic flow. And we can then, dig further down and look at the applications that are communicating across region. We can start to do risk analysis, understanding what tier, we have service tiers. And so we can understand the kinds of tiers that are communicating across and understand, is this risky? Should we talk to these application owners about actually sending this traffic cross region? Now, we talked earlier about fragmentation and how it's a known deficiency within our environment. And we just have to understand that. And we can do things like break this down on foreign kind of the NAT gateway. We can look at every single local application, split on it, and see which apps are actually using the NAT gateway. Right? This is just the understanding we have to have of that fragmentation, and know that this really isn't traffic talking to a NAT gateway. Right? It's talking through a NAT gateway. And then we can also look from the other perspective and see from the local application or the local kind NAT gateway where it's going to. So we get a really good sense of, A, the volume of traffic we're sending out to the internet. Right? Because we know that if it's going through a NAT gateway, it's going out to the internet. And we can understand that, from the volume perspective, which applications are actually doing so. Said there's a lot of advantages at the business level for this, but does this answer any of the questions I had or users brought to me on troubleshooting the network? In some cases it does. Right? The fact that we can look at actions actually allows us to see rejects. And so we can analyze data, we can look at applications and see like, oh, where am I getting rejects from? So that allows us to start troubleshooting some of the connection problems we may have. It also allows us to start looking at our dependencies on external services. And this is powerful, right? When you think about, every cluster in our environment uses some form of AWS service, SQS, SNS, right? SCS. Whatever it is, we need to understand what some of those dependencies are. And so through DNS crawling, understanding the IP addresses of all these services, being able to use that metadata, we can start to see which applications depend on SQS. We can see the volume of those. And we can start to understand if that breaks, what's going to happen? Which applications are actually going to suffer or be degraded due to that service not being available? Now, as an SRE, I also want to be able to answer questions I get daily. And with Sonar, we have IP metadata. We use it for dredge to enrich flow logs, but it can be used for other things. So for example, we use Slack. And the nice thing about Slack is you can build Slack bots. And so we built a Sonar bot. That Sonar bot listens for IP addresses, and instead of us having to answer, it does for us. So in this example, somebody's asking, hey, I'm seeing a large amount of requests coming from this IP address. Can anyone help? We can kind of nudge Sonar and say, hey, give me this info. Here you can see it responds with the fact it's a NAT gateway, the region, the NAT ID, the account it's in. Right? We don't have to do anything really. It's nice because it allows users to interact with this. We also have a feature-rich API that has the ability for programmatic access. There's lots of different applications out there that want to be able to use this, see what IPs are out there. They may do some metadata transformation at first where they grab a whole bunch of IPs and they want to know what they are. This gives us that capability. Now again, I'm an SRE, so I get troubleshooting questions a lot. And one of the things that I sometimes have to dig into is netstat. How many guys jump on boxes, run netstat out there? Yeah, me too. It's problematic, again, because I don't know what these IP addresses mean, just like flow logs. The same problem goes with this. I don't want to spend my time troubleshooting what these connections are, understanding what those IPs are. So luckily, we also have some scripting around being able to take netstat data and pump it out to a pretty table like this. Right? Now, I don't see IPs. I see directionality. I see what kind this is. Is it an instance? Is it an AWS service? If it's an instance, where does this live? What ASG is it in? What cluster is it in? Right? I get account info. I get regionality info. I get state, quantity. Right? Would this make it any easier for you guys to troubleshoot out there? Absolutely. Now, the biggest question we have, I know, when are you guys going to open source this? I want it. I could use it in my environment. And we're working on it. You know, one of the challenges we have is we have so many Netflix dependencies in it that we have to weed all those out. And we have to try to provide a product that would still work within your environment. Right? So we're working on it. You know, in the meantime, as a team, we love to talk to people. We love to reach out and, you know, understand, is there anything we're missing out of this? Or, you know, how could this help you in your environment? We are going to be at the booth after this. So if you want to stop by, talk to us about it, if you want to, you know, meet out in the lobby, we'd love to discuss this with you because, you know, we're solving some of the problems that we have. But, you know, there are things we might not understand or know. Or, you know, for example, the fragmentation problem. Someone may have solved that already and we don't know about it. So we'd love to come talk to you, or love to talk to you about it. So what's next? Where do we go from here? Does this provide enough information to be able to answer some of the questions that we have out there? And the answer is, unfortunately, no. Right? This provides a lot more insight into the network, the traffic flows that are going on, but it's really not enough to think about, you know, answering network weather events, for example. And so we want to take this a step further. You know, what we're doing next is really going to be setting up some eBPF on instance, grabbing an understanding of TCP state, an understanding of average round trip time, latency, right? Things like retransmissions, and pumping as further enriching those VPC flow logs with this data. And that's one of the next challenges that my colleague John Bennett's actually going to be working on here. All right, well, we appreciate you coming out and talking to us. Said, my name's Joel Kadama. You can see my email address is up here. Please feel free to reach out. Donovan?
Yep, again, my name is Donovan Fritz. Joel and I work hand in hand together. It's difficult in this type of theater to do open Q&A, so what we're going to do is we're going to kind of walk off stage here and feel free to come up and ask us questions. There is another event that we have to kind of clear out of here for, so if we get kicked out of the theater, then just meet us in the hallway, and then after that, we'll be at the Netflix booth in the Expo Center. So,
Thanks,
hope
everybody.
you guys enjoyed the talk. We'd love to talk to you some more about this.